slide, just give you a feeling for what we're going to cover today. We're going to give you an overview of the Paladin client. What is it? What it does? Very much a sort of feeling for what this project is. We're going to talk about models for privacy that are enabled via Paladin and how it enables those models and how they relate to the wider blockchain ecosystem. We're going to spend quite a lot of the session talking about the implementations of those models that come out of the box with Paladin. We call them the reference domains that are part of Paladin. And most interestingly, you're going to stop hearing me talk. I'm going to pass over to Andrew, and he's going to show you those in action. We'll then come back at the end to see how that comes all together. And we really hope to leave some time for Q&A at the end. But there is quite a lot to get through in the session, so we'll try our best to leave some time for live Q&A at the end as well. So, without further ado, let's talk about Paladin as a client. It's hard to think of one term to call Paladin. You know, we've heard it referred to as a node, as a vault, as a wallet. So let's just really talk about what it is and what it does. It sits on top of a EVM blockchain. It can be any EVM blockchain, no modification necessary to this. It could be a permissioned blockchain running Hyperledger Besu. It could be a roll-up as a service. It could be a layer 2. It could be a public mainnet like mainnet Ethereum or L2, as long as it supports running EVM smart contracts. And the types of smart contracts you'll be running on that EVM include everything that you're already running on that EVM and orchestration of atomic swaps. We'll talk about that at the very end. But most importantly, you'll be running private smart contracts. And the Paladin runtime itself is designed to give everything that's needed to run privacy-preserving smart contracts. And it turns out, regardless of what ecosystem you're looking at for a privacy-preserving smart contract, you need a lot. You need a whole client for orchestrating transactions onto the chain. We call it a connector, and Paladin contains the latest generation of a connector for EVM. It also contains all of the orchestration that's needed to allow multiple Paladin nodes to connect together and move through transactions. Indexing from the blockchain, event streaming reliably internally within Paladin and to applications, managing of transfer of data between Paladin nodes because this is privacy preserving, wallet functionality, to be able to have APIs for your applications to connect in, to transact, to listen to events, the storage and management of private data, because in a privacy preserving world, you can't assume that other people are looking after you for your data for you. You have to reliably look after it for yourself. Enterprise key management, and of course, then the implementations of privacy themselves, the off-chain part of the privacy-preserving smart contract. And maybe what's most interesting about Paladin is the variety of these that it supports. We're going to talk about the built-in versions that come of these reference implementations for zero-knowledge proof-based tokens, issuer-backed tokens, and private EVM worlds, similar to Tessera and Constellation that have come in the past, but also the ability to plug in all kinds of different privacy models as well. So that's what Paladin is. It's a runtime. It sits alongside the blockchain. It handles privacy-preserving smart contracts. Inside of Paladin, there's actually a lot of different components, and this session is not going to go through the implementation of these components in detail. But suffice to say, there's a JSON RPC API, very familiar to EVM programming, that you use JSON RPC, so we try to keep it as familiar as possible for that. An embedded user experience where you can get an experience, and you'll see this in the demo, built into the node. You can actually see what's going on. All of the heavy lifting engine, both the public connector part of it, but also the private submission engine, we'll see that later. We talked about the ability to index, the state storage, and then communication between nodes privately with a registry of what nodes you're talking to, backed by the blockchain, and lots of key management capabilities. But most importantly of all, the ability to package and run the code that's needed in lots of different forms according to like a standard Lego brick kind of plug-in mechanism to support all of these different ways that privacy-preserving smart contracts can work in EVM. And that's where we're going to really focus for the session in this bottom right-hand corner. So let's talk about what those privacy models are. This is the picture we're going to build up towards in this session, that in a world where you have a genuine shared ledger, not all privacy preserving DLT technologies tend to really focus on this idea of a shared ledger, but we're talking about a world where we have something like a blockchain, an EVM-based blockchain that we all share that gives us global state, this bottom layer. This bottom layer is going to be verified by multiple people who are not transacting. So what data can be written to this layer has to be verifiable by everybody who maintains this ledger. For sub-ledger privacy, that is transactions where the visibility of them is smaller, the data involved in them is smaller than the people who are maintaining this ledger, we need privacy-preserving smart contracts that have transaction-level privacy. And there's kind of three varieties of those we're going to go through. Zero-knowledge proof-based tokens, and you'll hear why I'm using tokens a few times as we go through, that tokens are very important because across the whole of this ledger, they are interoperable records of ownership of value that can be used and proved across the whole ledger. And there's two models for those that we're going to talk about, ZKP based and notarized. And we're also going to talk about fully programmable EVM smart contracts that run privately. And that might have been what you're expecting to hear about when you hear about EVM privacy, because that's really where EVM privacy has been for quite a long time. It's been just talking about these little private worlds. But what Paladin really focuses on is bringing all of these things together in a way that you can actually use programmable EVM worlds to program across these. And we'll come back to that a little bit at the end. So let's talk about where you might have imagined that we were going to be starting with an EVM privacy technology, and that is EVM private smart contracts or privacy groups. The implementation of this that's provided with Paladin is called Pente, and it is a privacy-preserving smart contract, just like everything else is in Paladin. But this one is about running EVM smart contracts in little mini EVM worlds, private worlds that are only visible to a small number of people. You can think of them a little bit like individual blockchains. They have a transaction history, they have a world state, it moves forwards, but it's maintained just privately between a much smaller set of people that have visibility to the ledger or maintain the base ledger itself. And the implementation of this inside of Paladin is really next generation. We're going to go through it in some detail in a minute. And it's the particularly unique thing about it is it's extremely lightweight. It can manage thousands, hundreds of thousands, millions of concurrent these little EVM worlds because it uses ephemeral EVMs, we call them, little runtimes that can pop into existence using the Besu library. They can pop into existence, run what transactions they need to run, and then go away again. And when they've gone away, they don't use any resource. A lot like a Lambda function would be in traditional Web 2 cloud hosting. And these run inside of the Paladin runtime. And we're going to see that in some detail. But these EVM smart contract worlds are great because they allow a whole blockchain to exist with a small number of parties. And all the data that's associated with that is locked into those parties. The challenge is that that does not work for tokens. This is really well established. My colleague, Jim Zhang, has actually written a really nice sort of article you can Google about sort of why you can't use privacy groups to put tokens inside of them. Because if you put a token inside of a privacy group, that token is stuck inside of the set of parties that are maintaining that privacy group and have visibility to it. A token needs to be interoperable across the whole ecosystem. And for that reason, tokens either work in one of two models. And this is pretty universal across all DLT and blockchain technologies. They either follow a model where you have an issuer, one particular party or decentralized group of parties that has knowledge and visibility of all of the transactions, pre-verifies those transactions, and then privacy and anonymity is available to anybody who's trading those tokens or holding those tokens, because you trust the issuer. Because you trust the issuer. And because you trust the issuer, you can trust any token. That's one model. The second model, which is possible, is you can trust every token because you trust mathematical proofs. You trust the math, or trust the maths. And in these worlds, using zero-knowledge proofs, there is no special role. It is fully decentralized. Because the blockchain verifies the proofs, you are confident that every transaction obeys the same rules, which means that anybody can present proof that they hold a token, and you immediately trust it without needing to trust any special party to have pre-verified it. And this is kind of where everyone would like to get to, but there are lots of practical considerations that mean that you might want to use either one of these models. There is no right or wrong between them. However, there's often been a challenge where you had to choose a whole technology stack that only supported one or the other of these models. So really what's interesting about Paladin is not that we've got the cleverest smart contracts for zero-knowledge proofs, although the ones built in are very good. It's the fact that it's not limited to just those smart contracts. And you can have lots of different implementations with different cryptography, all working together in the same Paladin runtime, and also interoperating with other models, like those issuer-backed tokens and like those EVM privacy groups. And that's why we get to this picture, where you can have all of these models existing on top of a common shared ledger, and you can program across them using these privacy groups. True programmable privacy, which is what we really need to get to. So that's an introduction of the different domains. I'm now going to try and give you a whistle-stop tour of how each of them works. Now, there is quite a bit of detail in this session, and probably each one of these could justify a session in its own right. So if you do find that you get a little bit lost, don't worry. We're going to come back up afterwards, and you're going to see them in action, and seeing them in action will probably help. And you maybe can come back to this section and some of the architecture docs in Paladin to sort of look in some more detail. We're again going to start with those EVM privacy groups, blockchain worlds that exist maintained just by a set of parties. And we're going to talk about the journey of a transaction all the way onto a blockchain and getting confirmed. And we're going to start from the fundamental model of the transaction as it's submitted. I want to propose a transaction. In the Paladin model, something that really makes it a significant step forwards from previous ones, the thing that executes this is called Pente. Pente actually means 5 in Greek, Tessera meant 4, so this is the piece of Paladin, which is kind of the next generation approach to what Tessera and Constellation before that did there. And in this world, there's actually a UTXO model of states, and this thing called an ephemeral EVM. I want to propose a transaction. What I do as the submitter in my Paladin node is I record locally my intent to perform this. My application has said that I'm willing to do this with this signature. And then I end up proposing a transaction, which is me spinning up a little EVM just from a library, a Besu jar library to start up an EVM. And it takes a traditional EVM representation of the transaction, and it runs using the available states as UTXO states from the local private state store that I know are available to be consumed. And each account has its own state. As it runs through the logic, it loads up the accounts that it needs. And it mutates those accounts, and it creates a proposal of a transaction that contains all of the account states that must have existed in that old state, everything else that I read from the blockchain, the new states that replace those account states, and the original transaction. And all of these are created in a privacy-preserving way. So that's my proposal for the transaction, but that's not enough. So if we zoom out and we put everything we just talked about in the top left-hand corner, we actually need a bunch more steps before we've got a transaction. The next step we need is this thing called a coordinator Very big piece of engineering. It's actually the single largest and most complicated bit of Paladin. We're not going to talk about it at all. And it is going to orchestrate everybody who's in that privacy group having the chance to verify that transaction. How do they verify it? They spin up their own little copy of an EVM, a Basu EVM. But this time, rather than trying to go and hunt for states to use to execute that transaction as an EVM transaction, look at the world based on the current state of the whole blockchain, they're going to just execute exactly what they've told they need to be execute. They're simply going to verify the transaction exactly as proposed. A lot like when you're forming a normal blockchain, you have a whole bunch of people validating the network. Everybody's executing and checking they come out with the same answers. And they generate a signature, which is their verification that this transaction obeys the rules of EVM. It's a signature saying, yes, that was executed correctly. And with those things in place, we now have enough to take those signatures and the coordinator can then submit that as a public traditional EVM smart contract transaction. And there's an EVM smart contract that runs in the actual ledger. And it verifies that all of those input states, the commitments to them, so these are salted hashes, this is not the data, all of those input states are unspent and available on the blockchain, that the signatures are sufficient to allow this to be confirmed, and generates the new output states on the blockchain and deletes the old states. And it emits an event. And that event is the only time at which this transaction is confirmed. So, unlike a lot of previous approaches to this, the blockchain is in control here. The blockchain is the source of truth. This smart contract executes. The event that comes out of this smart contract is what confirms for everybody the transaction. And actually, to generate the logs and all the traditional EVM smart contract stuff that comes out of an execution of an EVM smart contract, the receipts, etc., everybody runs it again at the end. Everybody can run this at any point, and it can be rerun at any point because they have a copy of the private data because they're in the group, and they have the blockchain record that this was a confirmed transaction. So this model allows a very scalable approach that actually is a step forward from previous approaches because it validates the inputs, the outputs, and the execution in the base blockchain. So that is the journey of a transaction for privacy groups, but that's not everything because we have these other models, these token-based models, and there's two of them. One is a zero-knowledge proof-based approach, and there's a pretty sophisticated implementation called Zito, which is actually a separate, maintained as a separate LFDT lab. Jim may do a future session talking about this in detail. And with a zero-knowledge proof approach, everybody can see every transaction on the blockchain, just as they could in the previous model, but the blockchain has a proof that is actually verified by the blockchain that all of the rules of this smart contract were obeyed. But this proof runs without the data. It just uses a hash of the data. And in this case, the data is coins, maybe fungible coins, maybe non-fungible coins. They can have all kinds of additional metadata as well. But fundamentally, they have an owner and a value. I, as party one, may know about the unmasked data of some coins, my coins, party one coins. Party two might know about the unmasked data of party two coins. But everybody can be sure that every coin is valid because every coin ended up running a verification, and the verification ran on the EVM blockchain. So everybody believes in it. But to be able to run a verification, you need to generate a proof. So actually, there's a very sophisticated proof engine that runs inside of Paladin, and this is very pluggable as well. Most proof generation systems nowadays are written in Rust. They can boil down to WebAssembly, and you can run those and execute them inside of the Paladin runtime very efficiently in their native WebAssembly form. There are also quite sophisticated things that these proofs might be doing beyond simple math. Maybe just a couple of examples from Zito, which are in the state tree that you're maintaining. Is somebody allowed to transact? Are they in an allow list? Have they been KYC'd and AML'd? Maybe there's additional stuff like read keys that are available to someone who's maintaining the network and wants to have a wider visibility into the transaction. And these things called nullifiers, which are very powerful, that allow you to mask the relationship between the states that exist, the UTXOs that exists, and the spending of them. So you can't even correlate and sort of reverse engineer the relationship between the states. So there's a lot of detail there that we're not going into, but these worlds of zero knowledge proof-based tokens are very powerful. The last one to go through at a high level before I hand over to Andrew to actually show you these in action is notarized tokens. Now this, again, it's just like zero knowledge proofs. It's sort of, there are whole ecosystems where this is going to be the only model of tokens that's available. And it's just one of the options inside of Paladin. And this is saying that there's actually some special party, maybe a party running off-chain logic, maybe a party maintaining a privacy group, maybe a party who's maintaining a privacy group between multiple parties, like an issuer and a regulator, but they have special knowledge. They're able to pre-verify all transactions. And by pre-verifying all transactions, everybody else can trust any individual transaction. This notary or issuer-based model is very powerful, but it still works the same way. Somebody proposes a transaction, it gets endorsed or notarized by a party, which might be doing it directly or doing it via an EVM privacy group. It then gets submitted to the blockchain, and the blockchain, again, is in control of the source of truth. A traditional EVM smart contract verifies those signatures, verifies the input states are available, generates the output states, and deletes any states that were previously available. So there's a lot of information there, but we've been through the 3 reference implementations and kind of how they work. So at this point, what I'm going to do is hand back to Andrew, and he's going to show you those in action.
All right. Thanks, Peter. I know we are going very quickly through a lot of concepts here. Like you said, I think we're going to run through everything, save questions till the end, but we will try to save some time for those questions. I want to highlight before I get into a demo here that everything I'm about to do, you can do on your own laptop. So developers and technical-minded folks, I would encourage you, particularly after this webinar, to find your way to the Paladin docs, and we'll make sure links are sent out after this. But there's a getting started guide that will help you get up and running with a local dev environment for Paladin. And there's also a set of tutorials that are going to cover a lot of the same concepts at actually a little more detail than I'm going to be able to do in this short session. So what you will get if you go through those, and what I've got on my laptop right here, Paladin is Kubernetes native, so it uses a Kubernetes operator and a number of custom resources to spin up everything you see on the screen. The first thing you get is a blockchain. In this case, by default, it's a 3-node Bezu blockchain. So you get a little private blockchain on your laptop with a very short block time to make development a little bit quicker and easier. And then, of course, you get Paladin nodes. So it'll also spin up 3 Paladin nodes that are sort of paired with those Bezu nodes. This would represent, at least a 3-party decentralized system where each party would be interacting with their own Paladin and Bezu node. In addition to being able to communicate with those Bezu nodes for shared data, the Paladin nodes themselves are also connected with a private data bus, point-to-point for off-chain data transfer over gRPC. And this is kind of a common architecture you've probably seen in many different technologies, where we have the blockchain for the data that should be shared with everyone on the network, and then we have a separate off-chain data bus for things that need to be shared privately. I have, as I said, kind of already run this. So just showing you kind of, I've got my Kubernetes cluster, I've got my 3 Bezu nodes, my 3 Paladin nodes. It has also deployed a bunch of smart contracts here. Zito in particular has many, many different flavors. So all these smart contracts are just kind of compiled and deployed for you out of the box. And then another thing that's going to be interesting as we go through is looking at the config file that's generated, just peeking into one of these Paladin nodes and the YAML config, many different config options for how Paladin runs. But in particular, I'm pulling out the domains section. Since the theme of this talk is sort of Paladin is not one thing, privacy is not one size fits all. The thing that the industry needs and the thing that Paladin is trying to be is a place that plugs all of these different things together. So we're going to be walking through these domains. By default, the Paladin node here is configured with the 3 domains we've been talking about. Noto is going to be loaded from this shared library. Pente is going to be loaded from this jar. Zito is going to be loaded from this shared library. So you can start to see how these things fit together, how they come into this runtime, and how we envision that over time, more and more of these domain plugins could be added for the next great privacy technology. So I think that's probably enough talk before I get into the demo itself. And all the engineers on the call probably perk up here. If you're not a coder, please stay with me. I'm going to try and jump back and forth between showing some code, showing a little bit of the developer experience, but also talking through some of the concepts that Peter covered in just a little bit more detail. I'm using the TypeScript SDK because I feel like it's an easy one to kind of put apps together quickly and see how some of these concepts work. And the first thing I want to do is just run a demo that is, what is Paladin out of the box before I bring in any of these privacy domains, right? Because these can get complicated. Peter showed a slide at the beginning just showing everything that's in the box with Paladin. And if I'm asking, what can I do with Paladin aside from all these privacy domains? The answer is sort of anything I can already do with EVM, but it provides transaction management, it provides key management, nonce management. If I'm dealing with a public chain, it provides gas management. So before we even get to privacy, there's a lot kind of in the experience that makes it a really useful sidecar or wrapper for an Ethereum node. In my code here, I've created 3 Paladin clients that are pointed to my 3 different Paladin nodes that I'm running on my laptop. And I've generated random users. So I'm just generating a random username, taking advantage of Paladin's key management functionality. So it's actually going to generate a public-private key pair for each of these random users. You can see here I've logged out the 3 users I generated, 1 at each Paladin node, and their public Ethereum address. Paladin's going to manage the private key that goes with that for signing transactions. Now, I could do things like, say, I want to deploy a smart contract. So I have a simple smart contract here. Everyone that's done Ethereum development has written one a bit like this. I just store a single value in the blockchain storage, and then I can go and retrieve the latest value later. Very simple contract. I compiled it ahead of time with Hardhat. So I have a compiled artifact here, and I'm just going to use Paladin's send transaction method. Now, under the hood, Peter mentioned that Paladin is based on JSON RPC. So all of these calls that you're going to see are just going to be JSON RPC calls, very similar to ETH send transaction. For anyone that's done programming against an Ethereum JSON RPC, we have Paladin transactions, PTX send transaction. So that's all that's happening underneath, but it's wrapped in a TypeScript API here. A bit different from normal Ethereum transactions in that I tell Paladin this is a public transaction. Now, the underlying blockchain might be private or permissioned, but from Paladin's perspective, this is a pass-through. It's not going to go through any privacy plugins. It's going to go directly to the underlying blockchain. So it's public from Paladin's perspective. I give it the ABI and the bytecode of the contract to deploy. I specify one of my generated signing keys, and then it's going to go ahead and deploy that. It gives me a UUID for that transaction, and I can use the UUID to look up the receipt. So this is kind of blockchain 101. That contract has been deployed. It went into block 3655. I get the transaction hash from the blockchain. Very similarly, I can use the same call to call into a smart contract. So if I want to call the store method and pass in a number to be stored, I can also use send transaction. In this case, I specify the function I want to call and the parameters to that function. I specify I'm going to send them to the contract address of that contract that was deployed. Again, sort of blockchain 101, I do store. That transaction confirmed very quickly because I have a short block period here, but that was stored in a block. So now I'm at block 3659. So that's been confirmed. And then finally, just like we have ETH send transaction, we also have a call method like ETH call. We have PTX call on the Paladin JSON RPC. So I can query into the blockchain, right? I can send things to be mined into blocks. I can also query the current state at the head of the blockchain. So I'm going to call the retrieve method on that same simple storage contract. I'm calling it here from Paladin node 1, but I can actually call it from Paladin node 2, Paladin node 3. I'll let this run on through. And the nature of the blockchain is that anyone can read that value, right? That's how blockchains work. Someone put the value out there, it was confirmed, it was added to a block, it's now part of history. Anyone with access to the blockchain can call into the blockchain and query that value. So that's sort of Paladin at its most basic. Before we bring any privacy into the picture, it does transaction management. As Peter mentioned, it can also do event indexing and many other sort of utility things on the Ethereum network. But that's, of course, not what's really interesting about Paladin. What's interesting is when we start layering privacy on top of this. So I'm going to roll right into the next demo. As I said, I'm going to do kind of small separate demos because of these things being separate concepts. We'll talk at the end how you tie these together a little bit. But say I didn't want to deploy that storage contract publicly on the blockchain for everyone to see. Say that maybe it was a negotiation for a trade between a couple of parties or an issuance of some security, right? It's some data that shouldn't be visible to everyone. I'm going to start my example the same way with 3 Paladin nodes, 3 random users, but this time I'm going to load a domain. So I'm loading the Pente domain here, and you'll see this key maps to one of the domains that has been configured in my Paladin node. Pente is going to load from this jar, and it's going to follow the domain interface that allows me to do a particular method of privacy preserving transactions. Pente, if you'll recall from the primer earlier, Pente is this world of private EVMs, ephemeral EVMs that are spun up and shared between a limited set of participants. So once I get my handle to that Pente domain, I'm going to call new privacy group. Again, just one more peek under the hood at what this SDK looks like. This is also calling send transaction. We've wrapped it in some layers of SDK, pretty APIs, but this is going to send a private Paladin transaction to that Pente domain. So this is not going to Paladin core, it's going to this plugin that was loaded from this Java jar. And Pente can do things like creating privacy groups, spinning up ephemeral EVMs. So I'm going to now interact with that functionality from the Pente domain. Again, we're going to go kind of quickly through here, but what happens is that I end up with a new instance of a Pente privacy group, which has its own unique address on the base blockchain. Everything that happens in an ephemeral EVM related to this privacy group will roll up to a set of hashes and account states that are committed to that base blockchain ledger. Like Peter said, the base blockchain is always in control here. So now that I've got a privacy group, I can kind of do some of the same things that I do on the blockchain directly. Within this group, I can call a deploy. Again, this is going to send a private transaction. I can pass the same ABI and bytecode from that storage contract, but instead of being deployed directly to the blockchain, user 1 is going to spin up an ephemeral EVM, run the deploy themselves. They're going to share that bytecode and ABI privately with the other members of the privacy group, in this case, user 1 and user 2. User 2 is going to do the same thing, spin up an ephemeral EVM. They're both going to agree on what the state of that is, and then the transaction will be committed to the base blockchain. Both of these members have agreed, okay, now we have a world state where this private storage contract represented by this bytecode is deployed at this address. And then they'll be able to transact going forward by doing things like setting a value on that contract. So here, again, very similar to the public EVM transaction. This is a private one where I'm calling into that privacy group, and I'm calling the store method, and I'm setting this number on the private address that both of these members agreed for the storage contract. Now I want to pause here and step back to show you kind of some of the things that are happening in Paladin. So I haven't shown the Paladin UI yet, but this is another thing that comes in the box. You can see that this store method went into block 3688. It has a blockchain transaction hash on the base blockchain. If I look at the details of that transaction from the perspective of member 1, who was the one that submitted this transaction, there's sort of a receipt that's a normal Ethereum receipt. There's also a private EVM transaction and receipt. So this is the result of that private ephemeral EVM where user 1 ran the whole thing and they stored it and they figure out what's the output state. How did accounts in that private EVM world change as a result of this transaction? User 2, because they're also part of this privacy group, is going to have the same thing. They have not only the resulting blockchain receipt, they have the private EVM transaction details that were shared to them. They verified these, they made sure it's a valid EVM transaction, and they committed to it. And between user 1 and user 2, this was added to the world state for that private EVM. Member 3, on the other hand, was not shared any of the private state data. So they know that something happened in a Pente domain, but they don't know what. They get a state receipt with just a bunch of hashes, right? They're meaningless hashes from this perspective for accounts that changed, but they don't have the bytecode. They don't have the details of what values were changed in that contract. That all was shared encrypted off-chain. And so member 3 can't construct the world state. So they effectively can't see this smart contract. A call in a private EVM works very, very similarly. So I'm going to call here from Paladin 1 and say, okay, I can query it. I have that EVM. I can spin it up. I can check the state. I can return it to you. Member 2, it's the same way. But member 3, if I attempt to request from member 3, hey, go spin up this ephemeral EVM and look at this address and call retrieve and tell me what value is there, I get a Java exception from the Pente domain because they don't have any of that data. They don't have the contract. They don't know what's been going on. They say, there's no contract deployed there. So that's kind of a very, very quick demo of how the private EVM world, these ephemeral Bezu EVMs, work to provide a functionality that's in line with things like Constellation and Tessera. I establish a privacy group. Only the members of that privacy group have the world state to run and query things from within that privacy group. I'm going to keep rolling straight on just because, again, so many things we want to show and pivot from sort of the world of EVM and programmable smart contract logic to the world of tokens. And I think, one thing that Paladin is kind of stating very clearly and that we think has been supported now in the industry is that tokens are different, right? It's not the case that you can say, I want to do private tokens by just putting an ERC20 into a privacy group. It just doesn't work because a privacy group means every member needs every state so they can build the state of the world. A token is something you want to incrementally disclose. You want to be able to prove that I own this token without telling you everywhere that that token has ever been in the world. So we are using these two domains, reference domains, Zito and Nodo, for kind of proving that pattern and providing a way for you to do token transactions with privacy. I'm starting with Zito, which is more complicated in many ways, but Paladin makes it really, really easy. And you'll see that kind of with the amount of code you need to write to do a zero-knowledge proof token here. Again, starting with 3 Paladin clients and 3 random users, but just a slight difference here. Part of Paladin's key management is that it does allow domains to bring their own key management and signing capabilities and add additional curves and algorithms for signing. It just turns out that for these zero-knowledge proof technologies, a lot of them use a different signing curve, in this case, the baby jub curve. So I can take that same user lookup and I can ask the Zito domain, can you generate me a public-private key pair using this other algorithm? So each lookup can kind of resolve into many different keys. So here's my baby jub keys. We're just going to see that these public keys are the ones that Zito uses more actively for tracking who owns what sort of value in the network. Again, I'm going to load a domain. I pass Zito, right, which is going to tell Paladin to load this bit of code here from this shared library. Once I have a handle to that, I can ask it to request that it creates a new Zito token. And Zito, because it is heavily paired with a piece of off-chain logic that generates a proof and a piece of on-chain logic that verifies that proof, you have lots of different flavors, and they have varying compute costs, varying complexities, varying privacy characteristics. We set up 3 of them in this config by default. I'm choosing the very simplest one, which provides basic anonymity and zero-knowledge proofs, just because it's the easiest to grasp first. There are many more complicated examples available in there and still coming, I'm sure. But once I've created one of these Zito tokens, I can then start interacting with it with a very simple sort of token-based API. Even though these are UTXO tokens underneath, they have methods like mint and transfer and burn that we're kind of familiar with from the Ethereum token ecosystem. So here I'm calling mint, and user 1 in this case is the owner of the Zito contract. So they're going to be the only allowed minter the way this is set up. They're going to mint 10,000 tokens or $10,000, whatever this may be, to user 2. If I look on my Paladin Explorer, I can see that user 1 has submitted a transaction, and the state receipt is interesting here. This is the UTXO state representing that new value. The owner here is that baby Jub key for user 2, and the amount is 10,000. So there's a new state in existence that has been created that is owned by user 2. It means they have 10,000 tokens. User 2, move my same bar. User 2 can also, of course, see that token that was created. And as you'd expect, user 3 cannot see it. They just see a state was created. They see the hash of that state on the base ledger, but they don't have the private data to know what that state means. Now, transfer is actually very interesting here. It's very similar. You can see it takes just a second to kind of generate that proof, submit it to the chain. A ton of stuff just happened in the Zito domain. A lot of math was done. Again, we could do a follow-on webinar just about that step right there. But suffice to say, user 2 generated a zero knowledge proof for spending that $10,000 token and transferring a fraction of it to user 3. The proof was verified on chain. We know that they're following the rules of the road because we trust these zero knowledge proofs. User 2 can, of course, see the full states that went into this. I spent a $10,000 coin. I gave $1,000 to user 3. I retained 9,000 for myself. The ZKP makes sure that this adds up, that I didn't create extra money as part of this. The interesting thing, of course, here is that user 1, even though they are the issuer or the creator of this currency, they don't know what's going on. They do know that the token they created has been spent. We'll talk just a little bit about nullifiers, which would actually allow us to prevent them from even knowing that. So you can take every little bit out of here so that they have less and less visibility. But they know just that something happened. They've lost visibility of this token because it's a ZKP token. So you can have these ecosystems where even the creator of the tokens doesn't have to be involved in every transfer. And we know that the transfers are following the rules of the road and they're democratic and decentralized. And user 2 and user 3 are just transacting directly with each other. I think I'm just going to pause there. We could easily fall down a deep hole on Zito. I think the only other thing I'll point out is that if I wanted, for instance, to use nullifiers, I say I don't even want the creator of a state to know when that state is spent. I'm gonna turn on nullifiers. I just choose that variant. I run the whole thing again, and it looks exactly the same, right? From a user perspective, user 2 got some tokens, user 2 spent those tokens. But when I look on the chain, the visibility of user 1 now is even weirder. What they actually have is a bunch of Merkle tree states. Again, can't go into it, but they don't even know what token was spent, right? It's anonymized another level where only the parties that are transacting actually know anything about what was spent or what was created. So again, just a very quick tour of one piece of this where I can do these ZKP tokens. Before I stop and try to pause with maybe 10 minutes for questions, I want to show the other type of token, which is Nodo. Another really common pattern we've seen in the industry. Again, many full tech stacks are based on just this pattern. Paladin is trying to take these patterns and bring them all together. So you don't have to pick just one. You tend to need 2 or 3 to build a real use case or ecosystem. It's going to start very much the same as the Zito example. I'm going to create 3 Paladin clients, 3 random users. Nodo is much more sort of just traditional Ethereum addresses and signing keys here. So I have 3 users with their public Ethereum keys. I'm going to load up my Nodo domain from the Nodo shared library. And I'm going to create a new instance of Nodo, which will get its own address on the base ledger, which again is where these UTXO records are going to be recorded. Nodo, I just have to specify a notary. User 1 is going to be the user that signs off on every transaction. They have full visibility. This would be your issuer, your registrar, your centralized party that is required to validate all transactions. We trust this token because we trust them. I'm putting it in basic notary mode, which means that essentially the notary is the only person that can mint. Everyone can initiate transfers. They have to submit them through the notary. and the notary will automatically validate conservation of value. That's sort of basic mode. Lots and lots of ways you can customize it. You can add tons of customizable EVM logic, policies, all of that is a topic for another webinar. But once I have my Nodo token, I can do a mint, very similar to the mint on Zito. If I go here, the notary, of course, is the one that approves these. So the notary is going to see the transaction, right? The user 2 here assembled a proposal. User 1 assembled the proposal and then submitted it themselves as the notary saying, I am going to mint 10,000 tokens to user 2. And user 2 as the recipient can see that they've received those 10,000 tokens. Transfers, of course, are a bit different. How transfers work is that user 2 wants to transfer tokens to user 3. They're going to do the assembly, but they hand it over to the notary. So they're going to send it through that private data bus to node 1. The notary is going to validate that they've followed the rules, that they haven't created money, that they haven't done their math wrong, that they haven't transferred to someone that violates one of the notary's policies. That all happens at the notary. The notary submits it to the chain. And of course, that means the notary can see the whole transaction. The notary knows the inputs, the notary knows the outputs. In this case, of course, user 2, who built the transaction, they know the inputs, they know the outputs. User 3, who received the transaction, knows a bit. They know the outputs because they were part of the outputs of this transaction. They don't know the inputs. They trust that the notary has validated those inputs. If there was a user 4 or user 5 here, they wouldn't see anything. So again, the privacy scope of this token is always going to be the transacting parties and that notary or issuer specialized party. I think I'm at time for my demo. So I am going to pause there, having give you maybe just a taste of these different domains. Paladin on its own for transaction management, the Pente domain for private EVM worlds, the Zito domain for tokens that are backed by zero-knowledge proofs, the Nodo domain for tokens that are backed by an issuer. And I'll end with just one quick sort of tease on, okay, I've got these individual things. What can I do with them? And this is the really true purpose of Paladin, and the truly interesting thing about Paladin is that it's not just one of them. And it's also not just all of them in separation, but you can, because everything rolls up to the same EVM-based ledger, you can orchestrate across them. So I could have a Nodo token that represents a bond. Maybe the issuer of that bond has a bit of programmable logic in a private EVM group with a sort of managing parties of the bond. And every time that bond changes hands, they run some logic for mint policies, for transfer policies. Maybe an investor is subscribing to that bond and they have a separate private EVM group where they're negotiating that subscription with the bond custodian. Maybe they're going to pay for that bond with some cash, and that cash is a ZKP backed token. I can take all of these things, I can do them together in a single EVM transaction, and I get this sort of holy grail of atomic settlement, where I can bring different domains and each party knows their piece of the transaction, and overall the transaction can be settled atomically for these DVP transactions. Again, showing how that happens together is kind of a next level once you understand each of the individual domains. How do I put them together into an atomic swap? But definitely kind of a tease for maybe future sessions. And again, I would encourage you to go through the tutorials, because the tutorials will walk you through some of these things, and a simple bond issuance example a bit like this. So that was a lot of ground. I'm going to stop talking, and I think for the remaining time on the call, we can just open it for Q&A.
Yeah, thanks, Andrew. And I wonder, Tomasz, did you want to pick a couple of interesting Q&A questions that are coming on the chat, or should we open it up to the floor?
No, you can absolutely open up the floor, Peter. We didn't have any specific questions on LinkedIn Live or YouTube, so it's your floor.
So, how do you want to manage it? Should people just raise their hands to ask questions, or?
Yeah, we have one hand raised from Bruno, so I can unmute him. And let's see. Bruno, you're unmuted. You can ask your question.
think, there we go.
Hello, Bruno. Okay, well, since you don't have that much time, I would suggest maybe Peter and Andrew, would you like to take a few questions from the Q&A box?
Yes. So can Noto and Zito be used together? So maybe I'll take this one briefly. Absolutely. And that's really that's what's interesting about Paladin, is not Noto in isolation or Zito in isolation, but the fact that they can be used together. And even more than that, and this is a real personal, from my perspective, when we talk about an ecosystem and value that comes from blockchain, it's about innovation, right? It's about doing things in a new way. And what's really interesting about Paladin is that you can have an issuer of something like a security that issues it using Noto. They can, as you saw from Andrew, they can maintain the issuance information privately, and they can do it in EVM using an EVM privacy group in Pente. They can then have that value exchanged for a cash-like token, and that could be a Zito token implemented with zero knowledge proofs. But now here's the really important part. Noto and Zito can exist in this ecosystem, and then someone else can come along and program new smart contracts using a combination of the base ledger, using maybe things like public stable coins, all of this kind of stuff, and they can program an exchange or a matching system, all these kinds of things, and they can perform privacy preserving transactions, and they can develop all of that EVM using some combination of public EVM, Pente, etc. The issuer that wrote the Noto coin, the central bank or the stablecoin issuer or the private bank, whatever, that created the cash token, don't need to change anything. And that new ecosystem can program across them. So that's how we think minimum viable ecosystems are really going to come together with privacy. It's the ability to program across them and innovate across them.
I think it's really interesting to call out too that we've shown interoperability with Paladin domains on this slide, but you touched on also interoperability with existing EVM, right? One of these pieces of the atomic transaction could be an ERC-20, it could be some other bit of programmable base ledger logic. So, and there's even, when you get into sort of advanced use cases, ways to convert Zito and Noto temporarily into things like ERC-20, right? So there's all this fluidity to move things back and forth and compose things together and choose for every single transaction, what is my privacy model and what is my feature set here? And how does that relate to other things that are all settling together on the same ledger?
So next question was, is Paladin the owner of the Pente privacy group, and what happens if Paladin 1 crashes? So I think that this is talking about Pente. So do you want to just come back to that, the slide on Pente that has all the mess of everything on the screen? So this journey is very complicated. A transaction going from being submitted to being approved by multiple parties, meeting a threshold of approval, making it all the way to the blockchain is complicated. There is no one owner of a Pente privacy group. There is genuinely shared ownership of that privacy group between the parties who are a member of it. But this system actually works a very different way to if you're familiar with Constellation, which didn't change when we got to Tesla. In that world, everybody pre-ran it, and then it sort of got executed in line with block formation at the end. It's not that same model. There's a much more flexible, it's actually a sort of multi-threaded, more scalable approach to this. But because it's more scalable, it needs this coordinator role on the left-hand side. And it's almost a little bit like blockchain consensus. It's not. We call it the decentralized sequencer algorithm. And it's a way that somebody gets high performance throughput. And you have to, it's quite clever because you have to like get ahead of the blockchain if you want to put lots of transactions into a block. You have to speculatively create a whole bunch of them. Now that's crash fault tolerant. We can talk about Byzantine in maybe a deep dive session, but that's a crash fault tolerant algorithm that coordinates that, allows shared ownership of the transactions, and allows crash fault tolerance of individual members. Have a look. Next question.
Peter, I'm afraid we only have time for one more, and then we're going to have to wrap it up.
Okay. So, how could I use the technology that Paladin incorporates for a high-value asset tracking process and logistics process, like containers in the SQL? Can be used for incorporation of private networks since you use EVM. Very new to this particular topic. Thank you for your response. I wonder, Andrew, do you have a minute for kind of like the high-level use case sort of side of this?
Yeah, and I know we didn't get into this sort of use case, right? We teased a little bit in sort of like plugging these things together. But yeah, Paladin can absolutely be used. I've been privileged at Kaleido to work with some groups like the Guardian Wholesale Network that are doing sort of investigation of using Paladin in real world use cases and how we apply that. Things like tracking high value assets. Yeah, you definitely, the model of Paladin is that you pick for each thing in your ecosystem, you know, what is the privacy model that makes sense? Tracking assets, those assets might be tokens, right? They might be some sort of non-fungible tokens, like a Zito token that is only visible when it's changing hands. They could also be a Pente privacy group, right? With a sort of, between the parties that are responsible for tracking those assets. They could be tracking, you know, each gate that they go through, and it could be both, right? So I think without, you know, getting too much into a particular architecture, it's all about breaking down your use case, thinking about what is the privacy model that matters to me, who are the parties that need to have access to this data, and then composing it together at I guess kind of a high level. And we'd love to do some follow-ups, and I'm sure Kaleido and Linux Foundation Decentralized Trust will be doing workshops and things like that where we talk more about those sort of things.
And do come and get involved. We have this little website that's a collection of links called paladinprivacy.org. It's just an easy way to find all the different things. But there's a Discord channel for chatting in the public, and you are very welcome if you want to talk about an actual use case to talk to us at Kaleido as well and request a briefing. But Discord's a great way to chat. GitHub is where you'll find the code, and everything that you saw Andrew do is just like a straightforward walkthrough that you can get by following through the documentation. You can run it all on your laptop. So really hope that we get a lot of engagement from you, and we hear about the things you're trying to solve and whether Paladin fits in as a part of the solution set.
Yeah, fantastic. Thank you so much, Peter and Andrew. And thank you everybody for joining. I agree, it was a perfect introduction to Paladin. And I see there is actually a lot of questions that still remain unanswered. And apologies for that. So thank you so much for Peter and Andrew to share this link to see where people can get involved, find out more, and just get their question answered. So thanks again to both of you, and thank you to Jim for answering all of the questions in the background, and Mark for organizing. And of course, thank you for our attendees, for our valuable audience. Before we go, just a couple of quick notes. So, there we go. So I would like to invite you to visit our event page to also see and sign up for the upcoming webinars, as well as the live events where we'll be present at, and you can visit our event page through these linked slides. I would also like to invite you to visit our meetup page to learn about the upcoming meetups and the workshops. And one of the following ones might be, as Andrew just mentioned, the deep dive into Paladin as well. So please stay tuned to this as well. Join our Discord community. There's a lot of real-time interaction going on there, and on these slides that Peter and Andrew shared, you can already find the how to get involved with Paladin on Discord. And for those of you interested in becoming corporate members, also feel free to email us at ecosystem@lfdecentralizedtrust.org or click this link. Before we go, just one last thing. The slides that Andrew and Peter were presenting will be available on our webinar library, so along with the recording. So in case you didn't manage to catch everything, or you would like to get all of that contact information. It will be available later today, so you can revisit that content. Thank you so much for joining us today. Thank you again to our panelists, and we hope to see you again next time.
Thank you.